So you can see that the previous podcast got cut off abruptly again by this bloody upgraded Windows system. Nonetheless, what I was trying to say before the podcast got cut short is that the curious thing about the chlorophyll is that it's about the only variable you can observe from space or from above that shows the geographical equator. If you look at winds, rain, clouds, humidity, and so on, you will always see the meteorological equator or the ITCZ as a dominant factor. Because of the Ekman divergence, upwelling, and chlorophyll being trapped to the equator, this shows up very clearly in satellite images. Okay, so let's look at the coupled ocean-atmosphere interactions again. We already looked at Bjerknes feedback in chapter 6, I think. So we will just touch on it again using this figure, schematic illustration of the zonal overturning circulations of the equatorial Pacific and atmosphere, which what we called as the Walker cell before, with warm sea surface temperatures, low pressure, rising air, deep convection, divergence at the top, and subsidence over the eastern Pacific, and the surface supply of moisture in the atmosphere and advection of waters westward in the ocean. Okay, so that's what is here again. Acronyms used are SLP for sea level pressure, sea surface temperature for SST, south equatorial current, equatorial undercurrent. The relative vertical scales between the atmosphere, sea surface slope, and the ocean are obviously significantly exaggerated. So ocean seas, anyway, you know why it is exaggerated, just to show this would be 10 to 15 kilometers, this is thousands of kilometers, so we have to just show it in this way. The Walker cell is 10 kilometer tall, while EUC is only 100 meter deep, and Eta only drops by 1 meter across the Pacific, going from here to there during an El Niño period. Asterisk represent the location of the zonal wind anomalies imagined later in this section we will look at. So, sorry, Eta is 1 meter on climatology usually, because cold waters, upwelling cold waters, low sea level, high pressure is compared with the warm sea surface temperatures, low sea level pressure, and high sea level. So if you go from here to here, it's approximately a rise of 1 meter, but during an El Nino it gets flattened because the warm water sloshes eastward, upwelling gets reduced, pressure gets reduced here, and so on and so forth. So here is our tropopause, which we remember is high in the low latitudes and drops off towards the east here, high in the western Pacific. So you have deep convection, warm sea surface temperatures, low sea level pressure that we talked about, and we have easterly trade winds which are causing Ekman divergence, upwelling, and cool SST here. Cool SSTs are associated with high sea level pressure as well, and we have the cool to warm sea surface temperature gradient reinforcing the zonal winds, where the Coriolis is low and pressure gradient can directly drive winds without worrying about Coriolis too much. And you have divergence at the tropopause in both directions and towards the poles as well, and that eastward branch of the Walker cell begins to subside over the eastern Pacific, reinforcing some of the ocean atmosphere interactions with stratus decks and so on that we will leave alone here. So the winds force the ocean to produce the south equatorial current, which is strongest south of the equator, and there is the north equatorial current to the north as well, which you're not mentioning. But the winds also create a pressure gradient from the high sea level to the low sea level in the ocean, so there is a eastward current that is directly related to the integrated strength of the zonal winds along the equator, which determines the sea level slope and the and the equatorial undercurrent. So there is the thermocline which is shallow in the east and deep in the west, as we've seen before, and the equatorial undercurrent is a very narrow strip of current which remains coherent because the eastward current is pushed into the equator in the north, into the equator in the south, to the right, to the left, so it can remain coherent along the equator from the west to the east, and it participates in the upwelling. It brings lots of properties from here as well, like nutrients potentially and so on, and the thermocline is held up by the divergence, and then the mixed layer processes are what we talked about before in terms of the kinetic energy of the winds, increasing the potential for entrainment and mixing, whereas the heating that is associated with the cold SSTs tends to stratify the ocean and reduce the entrainment turbulent kinetic energy available. We had talked about Bjerknes feedback as a positive feedback between the sea surface temperatures, sea level pressure, zonal winds reinforcing the upwelling and driving stronger winds, and during an El Nino, reduced upwelling, warmer SSTs, weakening the SST gradient, weakening the surface pressure gradient, weakening the winds, further reinforcing reduced upwelling, further reinforcing the warming, and then further reinforcing weaker winds and weaker upwelling and so on, which we called the Bjerknes feedback. We didn't say how this positive feedback, which keeps on reducing the upwelling during an El Nino and warming sea surface temperatures, and increasing the upwelling during La Nina and cooling the sea surface temperatures in the east, and reinforcing the gradient during La Nina, weakening the gradient during an El Nino, would terminate. Okay, so we need to invoke Kelvin waves and Raspy waves for doing that. So schematic illustration of an equatorially trapped Kelvin wave propagating eastward across the Pacific, warming SST, where mean thermocline is warming the SSTs where the mean thermocline is shallow enough. So typically you have a westerly wind burst that is associated with almost all the El Niños. There are many details about whether westerly wind bursts are part of the El Nino or they are just random forcings that happen all the time, and El Nino happens when other conditions are favorable, like the accumulation of the warm water that is being discharged by some other process. Many details. For this introductory course we are not going to go that far, but what we did see before was that the westerly wind bursts would produce convergence into the equator and divergence away here if we just look at the wind stress curl, and we had talked about how the convergence and the temporal spatial scales of the wind bursts, which means they are not steady winds, they come in, last for about a week, they are above certain wind speed like 8.5 meter per second or so, which is strong enough to force the ocean, and the ocean is forced not only by currents being pushed eastward, but also a wave packet gets generated which we called the Kelvin wave. So westerly wind burst would produce a downwelling Kelvin wave, which you can see is going eastward and producing a thermocline that was up here to progressively be pushed downward towards the east. So that means the entrainment cooling is reduced, so you can see that along the way you're generating warm temperature anomalies, which then become sea surface temperature anomalies by the time you reach here, and associated with that you have sea level anomaly as well. So deeper thermocline, higher sea level, which is fairly obvious. The other part is of course what we talked about before in terms of relative vorticity and planetary vorticity associated with this cyclonic cell here, which is going to propagate westward as Raspy waves, but it's starting far in the west, so there is the boundary right there. So somewhere here all this westerly wind burst thing happens when it starts, and then Raspy waves propagating westward are pretty soon going to hit the coast here, whereas the Kelvin wave propagates eastward by thousands of kilometers. And the other big thing we have to discuss is that the Kelvin wave, a gravity wave, propagates at about 3 times the speed with which the off-equatorial Raspy wave propagates. So the Kelvin wave will take about 3 months to go from the west to the east, and it will become coastal Kelvin wave, as we said, because it needs boundary on the right side in the northern hemisphere to build the pressure gradient and sea level to propagate, and to the left in the southern hemisphere, so it can go south and it can go north. But as the Kelvin wave is propagating north and south, it also disperses as Raspy wave off the coast. So those Raspy waves take 12 months to cross the Pacific. So winds can force Raspy waves here, but Kelvin wave can produce Raspy wave energy coming from westward from here. So all these processes are involved in turning off the positive feedback in the Bjerknes loop that we talked about, with upwelling sea surface temperature gradient, pressure gradient, wind anomalies, and so on. Of course, Ekman pumping is always involved. In the climatological case, Ekman upwelling is of course Ekman suction, because it's upward and bringing colder water closer to the surface, lifting the thermocline, and you need the mixed layer processes to entrain that cold water into the surface to cool the sea surface temperatures. Whereas in this case, anomalous Ekman pumping is happening. So convergence means downward Ekman velocity, so you can see Ekman pumping happening along the way, pushing the thermocline down and warming the subsurface and surface temperatures. So here are the maps of sea surface temperatures, rainfall in the climatology, and during an El Nino you can see that the warm pool has expanded eastward. The ITCZ has changed its shape here as well, and this happens, let's say, starting in about May, June or so, towards December, January, February. So the warmest waters here appear during December, January, February, as we said, which is what gave it the name El Nino, the Christ child, because it arrives during Christmas time and produces warm, nice, warm, balmy waters instead of the cold, usual waters. If we do the anomaly, so the difference of the El Nino temperatures versus the climatological long-term mean temperatures, we end up with warm pattern here, cooler pattern here, which is shape is related to the waves as well, which we will not worry about right now. But you can see the rainfall distribution has changed dramatically from being confined to the West Pacific and the ITCZ here to being spread out throughout, creating lots of anomalies up and down here, which are not visible at this scale. But you can see that the sea surface temperature map looks like this, and the precipitation anomaly map looks like this. Okay, the difference between these two. So you can see there is a significant increase in the anomalous rainfall, and there is a corresponding decrease in the ITCZ and the SPCZ region. And you can average the sea surface temperature anomalies over this box and plot it here for, let's say, 1980 to 2018 or so. So this is here going from December, never mind, the time period is not shown. So you can see that there are years when strong El Nino happens, like the 82 to 83 El Nino. You can see there are La Niñas, and typically La Niñas can last many, many years, as opposed to El Nino, which starts peaks and then terminates. So the 86, 87 El Nino, but there are times when El Nino can extend more than a year, like the 91, 93, 94, this is 94, 91, 93. This is the massive 97, 98 El Nino shown here, and there were little ones in 2002, I think 2006, 2010, and then this one also lasted more than a year. 2014 was a weak type of El Nino, but 2015 was a massive El Nino, and so on. So there are asymmetries in El Nino and La Nina, and there are dynamic reasons why that happens, which we will not go into in this introductory course, but I have discussed it elsewhere that you can follow up. So the summary of typical characteristics of oceanic, equatorial, and Raspy waves in this context, including their relative phase speeds, is worth looking at. Direction of propagation and location relative to the equator also are important. Kelvin wave, as I said, propagates at about 3 meters per second, whereas Raspy wave is slow, but its speed decreases as you go away from the equator. At 10 north, it is already reached a slow speed of 0.3 meter per second, as opposed to the equatorial Kelvin wave, which is moving at 3 meters per second. It's eastward or poleward, as we said. This is always westward unless there is Doppler shift where the background currents can push it eastward. And location is typically on the equator or along the coast, and during El Nino also it can be along the coast when it is strong, like you can see some evidence of the sea surface temperature spreading out here. That cannot happen by ocean currents because ocean currents move too slowly, but the wave can move very fast and push the thermocline down and produce warm sea surface temperature signals like that. Okay. Raspy waves, of course, are off the equator because on the equator F is 0. The restoring force for the Raspy wave is Coriolis or planetary vorticity, so needs to be in non-zero F, so off the equator. This is SST wind evaporation feedback, which I will do in the next podcast. So this is El Nino. Again, we took a slightly different perspective than other podcasts I have, or how we discussed the Bjerknes feedback. So, as I said, it's a very El Nino is a very complex ocean-atmosphere interaction process with timescales that are not always completely explained. We are often explaining what is happening rather than why it is happening. So there is still a lot of work to be done, of course. Okay.